Good morning, everybody. Welcome to Beijing. I'm Ming from Rutgers University and the Chinese Academy of Sciences. My talk today will, micro scale compared with what Randy has talked about. I'm going to focus on the optimal atmospheric CO2 concentration for the growth of winter wheat. I'm sure everybody here in this room heard about or have the concerns about global warming. The global temperature has increased dramatically and will continue to increase in the coming decades or maybe centuries. So most of you already seen those this picture, especially this famous polar bear. It's trapped on the ice piece. This is because the greenhouse gas effect. We all know the greenhouse gas effect works through, for the greenhouse molecules or the greenhouse gases, allowing the penetration of short-wave solar radiation and meanwhile intercept the outgoing long-wave radiation, makes the surface, the global surface warmer. So that's the basic idea of greenhouse gas effect. Here are the bad gas, the major three greenhouse gases, mostly carbon dioxide, methane, and nitric oxide, the N2O. So the three major ones contributed most of the greenhouse gas effect. So the concentration here, you see the, I wish I could see if I can move here. Yeah, you see the mouse. So the concentration of carbon dioxide in the past about 2,000 years, changing dramatically in recent decades. This is what we call a hockey stick. This figure looks like a hockey stick. So it's the dramatic jump here for the carbon dioxide concentration recently because the industrialization, the fossil fuel burning, is the major reason. We all know the climate change will cause severe problems in many fields, including the loss of biodiversity related to our public health issues. A lot of vector disease will be spread out faster to the new regions, and also with our agriculture part, causing famine or starvation in the future, also related to our water resources and the coastal region protection. In addition, also causing a lot of future climate change may increase the chance of what we call extreme weather, flooding, drought, or freezing. This is the picture I took years ago in 2008, just before the Chinese New Year, with the biggest ice and snowstorm in southern China. And also the sea level rising cause more problems, especially the coastal regions. The challenge with the climate change is so huge. So if we want, this is we know the IPCC, the climate change negotiations focusing on the stabilizing the future atmospheric CO2 concentration. We were talking about the 550 ppm. We call this is the CO2 equivalent, not CO2, just the CO2 concentration. We have to look at the peak. The global emission for the peak will somewhere a little bit after the 2020. So after this, the 2020, the global emission has to decrease gradually or quickly, actually. But based on the IPCC previous prediction, the prediction, this will be the A2 scenario. I wish I have a pointer here, but the IPCC predicted A2 scenario is one of the high scenario, gonna continue to increase the CO2 concentration by the end of this century. So the huge challenge here. So whether we are about the climate change, the climate has changed, or especially from the early 80s, right? In the past few decades, where we are. So we know in 1992, the IPCC made projections with the future fossil fuel emission or CO2 concentration. They have multiple scenarios. At that time, this is the highest one. The red line here is the A1FI, the highest scenario. At that time, people thought this is impossible. We better do something. So the next one is we call it the A1B scenario, which is the second line here. That most of the people thought we should be somewhere in the middle. Actually, in the past decades, look at the emission, the greenhouse gas emission, concentration. We are right on the worst edge here. Look at this. The dots are the real emission observations, and this is the project. This is the crisis, global financial crisis, caused a little bit of decrease with the precipitation, and then come back again. So this is the challenge is huge with the greenhouse gas emission and greenhouse gas control. And even look at the sea level rising. That's another indicator for climate change or big concern with the future sea level rising. Again, that's the prediction with multiple models. And the black line here is the observation, is the satellite observation, the data again is on top of the prediction. So all those evidences have showing climate change actually is even worse, or at least on the worst situation we have predicted. It's a huge challenge here. But today I'm gonna focus on the agriculture part. Atmospheric CO2 concentration, this curve shows from the early pre-industrialization to the current level, and also for the future to the 2300. This is based on the most recent IPCC model prediction. The highest scenario is the RCP 8.5. So the future global CO2 concentration could reach about 2,000 ppm by middle of the 2200s, if the worst situation. But this could happen if in the past decades we already see the worst situation happen. We know CO2, well, that's the bad part, but CO2, the carbon dioxide, is not always bad, right? We know CO2 is very important to us. It's the frame of life, actually, right? It's the carbon. That's the very important element on the Earth. CO2 fertilization effect, I'm sure many of you heard this term, which means we know carbon dioxide is the food for plants. It's the fundamental material. Through the photosynthetic, this chemical reaction, very simple reaction, but it's the most complicated, probably the chemical reaction in the world at that larger scale. So the raw material is for photosynthesis. And also high CO2 concentration will cause a higher reaction rate, increasing the photosynthetic rate, which is good, right? So the CO2 fertilization effect. And this has been confirmed by many experiments and also by many models. The CO2 diffusion, higher CO2 concentration in the atmosphere will causing more molecules diffused into the leaf through those little aperture we call the stoma, right? Stomata. And so the higher concentration will have more diffusion, faster diffusion process will increase the photosynthetic rate, which is very straightforward. But here is the tough part is how to make the balance, the net impact with the climate change, increasing temperature, changing the precipitation pattern, all will affect all agriculture. The other part is CO2 fertilization effect, right? Which is a positive, it's the good part. So how to balance those? It's tough. We need to make a good decision with the future climate change decision, we need to balance this. But I'm not gonna tell you today who is the winner. I'm gonna focusing on this, the CO2 fertilization effect. With the increasing the CO2 concentration will causing higher photosynthetic rate. But will this sustain like a linear model, like a curve trend like this, will continue? Or will the CO2 fertilization effect pick up quickly in the initial increase of the CO2 concentration and then gradually level off quickly? Or even worse, the fertilization effect pick up with the increased CO2 concentration to some point change the direction. The direction we call it negative CO2 fertilization effect declines. Which one will happen? So I think that's a big concern here. So that's one of my studies recent years of focusing on this to look at this, how the CO2 fertilization effect will on different plants or different crops. So this is what we call the CO2 fertilization saturation effect. So the higher CO2 concentration like this one will level off quickly. So continue to increase, they just stabilize. This has been, for the smaller scale, leaf level scale with the ACI curve has been confirmed for many years. This is the NASA, the biomass growth chamber, production chamber showed their results. This has been done many years ago. They showed also for the wheat crop. The CO2 fertilization effect can sustain up to 2,300 ppm, which is very high. So which means they stabilize, they increase quickly, stabilize around 1,000 ppm and then level off all the way to 2,300 ppm. So that's not a big concern. We will definitely, the previous figure shows by the the future climate or worse situation, probably the atmospheric CO2 concentration could increase somewhere about 2,000, but still within that level, right? But this is a review paper summarized by Amthor years ago, who all the experiment data together found, this is for wheat, also for wheat, for the CO2 fertilization effect may peak only somewhere about 890 ppm, which is much lower, which means after this concentration, the negative effect will appear. So this is my question here. About winter wheat, where nobody have actually this Amthor's paper is just it's not experiment, it's just a review, it's a hypothetical speculation. Nobody have done the experiments to confirm this. Will this happen or not? Most of the CO2 experiments in the past decades are focusing on doubling CO2, doubling from 350 ppm or increase from 500 ppm or 600 ppm. Not multiple levels concentration. So we did an experiment by controlling the CO2 concentration at multiple levels using growth chamber at Rutgers University. Also, we're using the pots, the PVC pipes to plant. We have 8 pots in each chamber. We have 8 growth chambers, controlling the CO2 concentration at 5 levels, basically 400, 600, 800, 1,000, and 1,200 ppm with the 5 growth chambers. And also we're using the CO2 cylinder. The high purity CO2 source is essential because you don't want your plants being polluted by other chemicals in the gas. So we also developed a automatic control system to control the CO2 concentration at our target level. Using this is the conventional big growth chamber, walk-in chamber. Other environmental factors we control in the chamber, including temperature, we control at 21 degrees Celsius, humidity between 60 and 70%. Light intensity is enough, about 1,000 micromole is a photon. The photon is part. And for the light period, we give the plants the light in early morning, 6 o'clock in the morning, and stop the light at 8 o'clock in the evening. Soil, we're using treated clay, and also we water the plants every other day. Water, we just using plain water. Also, we fertilize the plants with using the half-saturated Hoagland's solution once a week. So this is the plants we grow there in the growth chamber. This is about during the growing period, we keep measuring the plants with the growth, with all the many factors. So we have a lot of replicas, about 8 PVC pipes, the pots in each chamber. So we did a lot of measurements. So also we measure the stomato using the nail varnish to measure the stomato density and the stomato pattern. They were using the microscope imaging system to look at the stomata. This is what we did, looked at the stomato pattern. and using the software for analyzing the stomata size, the length, and the distribution. Also, we're using the liquid photosynthetic system that want to measure the leaf level photosynthesis. We measured at the growth concentration, the CO2 concentration. If the plants grow at 800 ppm, for example, we also measure to control the photosynthesis at 800 ppm to match the growth ambient CO2 concentration. At the end, we grew the plants to 5 weeks, about 35 days, and then we depotted the plants and measure the above ground biomass, the below ground biomass, basically the roots, and the total biomass, and also we measure, using oven dry, all the common procedures, but a lot of work. Students helped with those. Also, my daughter helped with the work on the weekends. And here are the results. I want to tell you the story, what we found here. So, effects of CO2 enrichment on the biomass growth of the winter wheat. There are 3 curves here. This is the green one is the above ground biomass. The red one is the below ground, the root biomass. The black one is the total biomass. I want to explain a little bit. Look at the total biomass increase with the CO2 concentration. The x-axis is 400, 600, 800. Increase quickly to 800 and here. And after this, the decline a little bit, and to this 1200 ppm dramatically declined. This is the total biomass. So as we fit this with a quadratic model, found the CO2 peak, which is basically is the optimal CO2 concentration. It's about 900 ppm, which is very close to Amethyst speculation based on the review paper. But it's much lower than the NASA's growth production chamber they did in the 90s. So they found it's much higher. So basically they found a level off. They didn't find the declining part. So this gives us the risk, say positive climate change, if the CO2 concentration go to very high, beyond 900 ppm, could hurt our plants. Not just the positive CO2 fertilization effect will decline or eventually disappear like this. So this is what we looked at, the quantified CO2 fertilization effect using the carbon gain per unit or per ppm increase in CO2 concentration. So of course, in the lower concentration, 400 ppm to 600 ppm, with the increase of the ambient CO2 concentration, the CO2 fertilization effect declines linear, quickly, like this. Beyond the 900 ppm here, we see the negative fertilization effect. So becoming negative. So this, again, as I mentioned, this is what we are concerned about. A future very high CO2 concentration may hurt our winter wheat. We also looked at the other characteristics of the plants, the height, the leaf characteristics, width and length. We found that the CO2 concentration actually has a little effect on the plant height and the leaf length, but have a little bit impact on the leaf width, but not huge. For the growth, those indicators not much affected. But how the biomass changed, right? So why the biomass changed? We want to understand what caused the biomass change, that curve, that bell-shaped curve. We also looked at the stomatal density on the leaves on both the abaxial and adaxial sides of the leaf. We found the stomatal density dramatically decreased with the increase of CO2 concentration, which means higher CO2 concentration causing smaller amount of stomata on the leaf, which makes sense, right? So the lower CO2 concentration, when you need more, the plants need more stomata for CO2 diffusion. And with a higher CO2 concentration, they don't need them. They just close the doors. So the decrease of the stomata density. Also, we looked at the stomatal size, the length of the stomata. So found that the stomata length actually increased in the beginning with the CO2 concentration, reaching somewhere the maximum around 800 ppm, the stomata length, the size. So even that means in the early part of the CO2 increasing, the stomata density decreased, the number of stomata decreased, but the size increased, the length increased. But with further increase of CO2 concentration beyond 800 ppm, even the stomata, the length, the size also getting smaller. Not just the stomata, the size changed with CO2 concentration. We also found that the CO2 concentration can change the stomata distribution pattern on the leaf. The pattern here I want to explain that we looked at 3 patterns. One is the random pattern. The stomata on the leaf surface is just randomly distributed, right? Random pattern. Or the regular pattern. It's a regular pattern is the rows and columns are very regular. So like this, when we're using the spatial statistical approach, we're using the replace K function. Look at this one. If the L height value is between, we're using the Monte Carlo simulation for 100 times, between this is the upper 95 envelope, this is the lower 95 envelope. Between the 2 envelopes, those 2 lines is random pattern. And the x-axis is the scale. At a different scale, we looked at a different scale how the spatial pattern change. So we found at the smaller scale, the stomata is distributed spatially more regular. This is the regular pattern. And this is a random pattern in this part. And go to larger scale, the stomata becomes cluster because larger, the vines or the leaf vines may separate the stomata, causing the cluster. So we know that for the diffusion, either for CO2 diffusing in and for water vapor diffuse out, right? The more regular pattern reduces the resistance, more regular pattern. So we do found the CO2 concentration increasing, causing at a smaller scale, the stomata be more regularly distributed, more regularly spacing distributed. So this will reduce the diffusion resistance from the stomata to the reaction center, which is the chloroplast, right, for the photosynthesis for CO2. So that's the distribution pattern. This is the first time we found the pattern change. We also want to look at the other factors. What caused the biomass change? First, we thought is the photosynthetic rate change. Must be related to photosynthesis, right? We did find that the leaf net photosynthesis increased dramatically with the increased CO2 concentration from 400 to somewhere the 900, more than 900 ppm somewhere here. But after the 1000 ppm, after this peak, the leaf photosynthesis also started declining. So it's matching the biomass curve we observed. So this confirm the photosynthetic rate is a big factor on causing the declining part. We also looked at the other part. For the photosynthetic change, we want to know which part caused the photosynthetic change. Is the CO2 diffusion process, or is the chemical reaction, the carboxylation, or the efficiency part change, right? We looked at the diffusion part, we looked at the CO2, the stomata conductance. Look at the initial increase of CO2 concentration from 400 to 600 ppm, the stomata conductance, declined a little bit. But with a further increase beyond, say, 800 or 1000 ppm, the stomata conductance dramatically declined, about 30%. So that means the CO2 diffusion process was involved with the biomass curve, right? Involved with those, also with the photosynthetic efficiency change. Further, we looked at the carboxylation process, which is the biochemical process. The VC max is the maximum carboxylation rate. Basically, it's the Rubisco efficiency here. We want to look at if the Rubisco efficiency changed under higher CO2 concentration. Interestingly, we found the VC max also increase with the CO2 concentration in the early stage, and reaching a peak and then declines. And this peak, look at this peak, also match pretty well with the biomass peak, around 900 ppm. So this is different from the earlier studies. Earlier studies saw that the higher CO2 concentration will cause the Rubisco concentration and activity declines. But we found actually increase with the early increased CO2 concentration. But beyond the turning point, started to decline. So this is different from early studies. This is more complicated with the carboxylation. For the increasing part is we think is it's a review paper by Steve Long, and he looked at just looked at efficiency, looked at just by the Rubisco efficiency. He did a projection. Is our results actually increasing the total biomass from 400 ppm to 800 ppm by about 100% total biomass, 97%, very close to Steve Long's theoretical prediction, based on Rubisco property. So this carboxylation process involved. Also, we looked at the other process, is the photochemical process with the electron chain, transport chain, if that is involved. We found that the GMX also increased, but be more complicated. So the GMX have a trough here, a little bit decline from 400 to 600, but then increase and reaching a peak at more than 1,000 ppm, but this is a higher peak here. It's a different story here for the photochemical process. The electron transport process is being involved, but it's different from the carboxylation process. So this, we also looked at the balance between VCMax and GMX, which is the balance between carboxylation, biochemical, and photochemical, which those two major processes, how they are involved. We looked at the ratio of VCMax and GMX to represent the balance. We also found the ratio increase at the lower concentration, reaching a peak and then declines. So this means the two processes are unevenly affected. With the increase of the CO2 concentration, the carboxylation process increases more than the photochemical process. But with a higher CO2 concentration, the very high, the carboxylation is being hurt more by the photochemical. That's causing the decline of this part, the imbalance between those two those major processes for photosynthesis. And here is the take-home message, what we have found based on this experiment. We found that the CO2 have fertilization effect. It's not just saturated, reaching a peak around 900 ppm. Beyond this peak, the biomass, the growth actually started declining dramatically. This peak is much lower than previous studies. One of the studies reviewed the weight they found is about 1,200 ppm. And many greenhouse growers, actually, if you look online, they recommended the CO2 concentration between 1,000 to 1,200 ppm. Also depends on your plants. For some plants of tomato or some plants, if you increase the CO2 concentration too much, they get crazy. But most of the plants, they will respond with the fertilization effect. We boost their production. The growth grow better. So further increase with the CO2 concentration beyond this point will cause the decline. So the early part, the CO2, the positive fertilization effect, what we have found is much stronger than the previous study. So the review paper on the winter wheat published last year found is 28%. We found it's about 100%. And based on the phase experiments, they found only 20% for C3 plants, and about 32% based on the OTC, the open top chamber studies. Or study the growth chamber shows much higher for the vegetative growth. This is not the final product. It's just the biomass. Elevating CO2 concentration not only reduced the stomatal density and the size and stomatal conductance, but also changed the spatial distribution pattern. This will lead in a more regular pattern at a higher CO2 concentration. So what do our results mean? This means the winter wheat may get hurt first in the future with a very high CO2 concentration. But our results may also suggest for future selecting the species or for breeding the new cultivars, may targeting the species or cultivars with higher optimal CO2 concentration to reduce the risk and the future climate change. Okay, as an indicator for breeding, for breeders. Also, our results is, as I mentioned again, it's just the biomass. It's not the economic, the yield. So, but this is the critical, the important part, is the base for the yield. So because we're using growth chamber, we lacking the chilling period. You cannot grow them too long. I want to acknowledge our collaborators, Bingru Huang and Drs. Yali Song at Rutgers University helped with the design experiments, and also Patrick Burgess and helped with the experiments, managing the greenhouse chambers, and also the USDA support this work. And thank you all for your time and attention.
Thank you very much. And I think we are actually quite well on schedule, so if there are questions, we can ask them. If somebody has questions to me with my speech, contact me later. I forgot that. But here, I have a question. Yeah, so what do you think about these phase experiments, which have been done with several crops, and I think also winter wheat? Is that in line with your data? Also, growing wheat in the field with these raised CO2 concentrations?
For the phase is phase is the free atmospheric CO2 enrichment experiments over the world. There are many dozens of phase sites, including the crops. Our results actually from 400 to 800, doubling. From the early phase only from 350 to 500 ppm, most of them, or some of them 550, or some, nowadays they increase, but not too high. The phase results shows only an increase of about 20%. 20%. Our results shows much higher because our CO2 range is higher. We doubled from 400 to 800. So look at that part. So it's much higher. But the consistency has been found with the very strong CO2 fertilization effect in the early part. And but the phase, as I mentioned, is they only have 2 CO2 concentration: current, ambient, and either 500 or 600. So, but the phase has the advantage. It's more natural. It's open, where you can grow the plants with all the developmental stages. For the growth chamber, we can only look at the part, only about a little more than a month. So that's the limitation.
Yeah, exactly. Seed yield as a grain, that would be something which is missing in your studies, right? You have biomass, but you don't have the grain.
Right. Yeah, we can only tell you the biomass, but for the phase, I think controlling the very high CO2 concentration. Actually, we are working on the next level with even higher CO2 concentration or multiple levels to see the response. We found that actually the rural biomass increased more than the above ground. So it's changing the above ground and the below ground allocation pattern also. So that means the total biomass increased, but more may allocated to the rural system, not the grain, not the yield. Yes.
I have a question about, you were mentioning that in the greenhouses they recommend 1,000 to 1,200 ppm, right? That's what you said generally.
Yeah, we increased from 400 to 1,200, that range. Yeah.
But your results are based on your wheat study, so can that be applied to other crops, or someone has to study every crop and figure out what is optimum for that crop?
Good question. Actually, to my knowledge, not many studies on the CO2 fertilization effect look at the multiple CO2 concentration. That's why I sent the paper out a few months ago, and the journal editor accepted quickly, said, "Oh, this will be our significant understanding for our field in the future for the CO2 fertilization effect." But I think this approach definitely can be easily extended to the other crops. But this is C3. We know it's more winter wheat. C3 plants is more responsible to CO2. But for C4 plants like the corn may respond less, but it depends, But definitely also the phase experiments also show even the C4 plants response dramatically. So the photosynthetic CO2, will stimulate carboxylation and meanwhile suppress the photorespiration. That's why, you see the very strong effect. Yes?
Increasing carbon dioxide concentration also increases temperature. But you said in your experiment you have kept it constant, 21 degrees centigrade. So how is it possible?
Very, very good question. Actually, that's again, we talk about the multi-factor experiment. This back years ago, the phase is being shut down, right? In the many, the big one is the Duke Forest. It's a big, it's very expensive phase project that's running for more than 10 years, and they shut it down a few years ago. And because it's a single factor, we can only look at CO2 effect. But the future global warming comes with CO2 concentration increase, increasing temperature, changing precipitation pattern, and plus others like ozone, some areas, ozone pollution or multi-stressors together. Who will be the winner? It's very, very difficult. Years ago, the NSF from the US, the NSF came to China in Shanghai. We had a meeting here, talk about the collaboration with the multi-factor experiment. Well, that time we not the crops. We talk about the big forest. We talk about the tropical forest. But the technology is mature, is getting there. For let's say the big trees, right? You want to using the fish, it's okay on the trees, but how can you control the temperature exactly to 2.5 degrees Celsius? It's very, very difficult, and also very high energy demand. We did a calculation to do our piece of forest experiment. We need a run just for the experiment. The energy supply, we need a single power plant to supply the energy. So it's very costly, more than $1 billion, the total experiment on running on that one, with temperature, precipitation, nutrients, and CO2, multiple experiment. But on the crops, I think it's much easier. The story will be more difficult. Definitely will change the picture if considering the interaction effects. So there are some experiments with increasing temperature, increasing CO2, but multiple factors is getting more difficult.
Actually, there is a wide range starting from 400 ppm to 200 ppm in the concentration of carbon dioxide in your experimentation. So to what extent that increase in temperature was there in different fuel chambers because of increasing CO2 concentration?
You cannot take temperature is constant.
So we just hold temperature as a constant in this experiment, but the temperature and the CO2 interaction effect is this what we call it is the direct effect, is the CO2 direct effect. The indirect effect is through the climate change, the greenhouse gas effect. So that part is getting more difficult to, just based on the model projection. Experiments using the infrared heater, they're using the light infrared heater to heat the plants. We run one in China for years in two places on the crops for the increasing the temperature using infrared heater. But we don't have the one with multiple factors with CO2 and the temperature. It's a good question.
Last question.
Thank you for your research work.
Thank you.
I think your work is theoretical rather than practical. I think we cannot reach this concentration, which you recommended, the optimum one, which is 900.
About 900 ppm, right.
So I think it is just a theoretical experiment rather than practical, because other factors affect the growth. Temperature, rising temperature, low precipitation will affect
well, they will suppress. They will, let's say, for precipitation. Actually, that's another factor. I just mentioned the fertilization effect. Another coupling factor is what we call the water use efficiency. Increasing CO2 concentration will increase water use efficiency also. So in the dry environment, actually increasing CO2 concentration not just have the direct carboxylation effect, and also can help the plants saving more water, improve the soil water condition. So that's even more complicated. I didn't mention this part. So that's, but 900 ppm is a turning point. But where we will go in the reality in the future, I don't know. If depending on the current political system, if the global climate change negotiation achieve the goal later this year, November in Paris, right? We may avoid that high concentration. But if we go what we call a business as usual, we could well beyond that point in the next century.
So thanks a lot also for the questions.
Thank you.